Okay, thanks. So, let's see. Okay, so first thing, let me point out real quick two things. First is that this the book by the set of lecture notes by Cheeger, which were sort of recommended, is not in the library, I think, but there is an online copy. I think if you Google it, you'll find it. And second is that the syllabus for today seems to be a little bit off. It's saying that Jacob is going twice. It will, in fact, be Jacob and then Hayo today. It'll always be me, Jacob, Hayo, except possibly on Wednesday. There are disagreements on who gets to go then. Okay, so what are we talking about today? So for 2 weeks now, we're going to discuss Ricci curvature and the various aspects of it. So I'll outline for you today more or less kind of what I want to cover over the next couple of weeks. But maybe a good place to start before I get into any of this is just to sort of say, who cares? So I mean, Ricci curvature, it's a fairly popular topic right now, but why? I mean, what's the motivation? And there's a lot of motivations coming from different directions, but if I were going to give you sort of a 25-word or less reason as to why one studies Ricci curvature, I would start with the following. I would start with let's look at curvature first, right, before anything. I mean, I'm kind of hoping that we all know what a Riemannian manifold is, so I can just say that's a Riemannian manifold. So if we have a Riemannian manifold, what's the curvature? I mean, I can give you a definition. It doesn't help you much when you see it the first time, but you can give it. So I mean, if the curvature is it's a 3-1 tensor, right? So it means that if I take 3 vectors, it gives me a vector. And it does it just by looking at the Hessian in the xy direction of z and subtracting off the Hessian in the yx direction of z. Of course, on Euclidean space, this is 0. On a general Riemannian manifold, it is not. And so you simply write the thing down, and you define that as being curvature. Fine. That's curvature. Now, that's a useless definition. I mean, it doesn't tell you anything, right? I mean, it does sort of, it tells you everything important about the geometry, but why is not so clear from this. And in particular, I mean, I'm an analyst, and most of what we'll be doing for 2 weeks in here is geometry and analysis. So why on earth does this have some sort of relation to analysis? And just from a moral perspective here, the point is this. How should you view this thing? I mean, it's a 4 tensor, right? You should view this thing as being the Hessian of the metric, right? So it's like you take a function, you take 2 derivatives of it. This is like taking the metric, Gij, and taking 2 derivatives of it. Now, of course, if you actually take the Hessian of the metric, you get 0. So this isn't a literal thing. But one should view this from a moral perspective. In particular, if I hand you a Riemannian manifold and I tell you the curvature is bounded, then you should expect the metric to behave like a function on Rn with two derivatives bounded. I mean, if I give you a function Rn and I say 2 derivatives are bounded, you fully well expect it to be well behaved. I mean, there's all kinds of nice behaviors. And you should expect the same from a metric. Now, this is a little more complicated. You can't just go picking your favorite coordinate system and saying this is true. What this really means is kind of up to gauge this is true. And in particular, you can find a coordinate system for which this thing looks like a function with 2 derivatives bounded. In particular, you can well imagine the analysis now becomes well behaved, and you can do all kinds of wonderful things on such spaces. So fine, that's curvature. It's like the Hessian of the metric. But now if we look at Ricci curvature, and again, let's give a definition. What do? We take some orthonormal basis, EI at some point, and we sum. So this is to say we trace the curvature. The trace of the curvature is the Ricci. Fine. But now, I mean, if we're viewing the curvature operator here as being the Hessian of the metric, then when we go taking a trace, suddenly this should be telling us that we're viewing the Ricci curvature as being the Laplacian of the metric. And this is very much true. And in particular, I mean, this should, I mean, basically with no other words said, this should give some motivation as to why Ricci curvature appears everywhere. I mean, the very first thing you do when you start analysis, you start studying Laplacians. They appear everywhere, in math and physics, whatever. So it's not surprising that if you want to study Riemannian manifolds, that what should count as the Laplacian of the metric should appear everywhere. And it does. And that's basically why. Actually interpreting this as the Laplacian of the metric, we'll see, is more subtle. The problem is that you can really legitimately do this if you make more geometric assumptions, like a lower bound on the injectivity radius. It really does behave like the Laplacian of the metric. But otherwise, it's really just sort of it's a nonlinear version of it with an infinite dimensional gauge group. It's a little more complicated, but the moral is there. It tells us where to start. Okay, fine. So then once we have Ricci curvature, what we'll be studying over the next couple of weeks are sort of various conditions on Ricci curvature. So the three that will play the most important role is we can talk about lower bounds on the Ricci curvature. So what does that mean? That just means, this is a 2 tensor, right? So it can have lower bounds on the eigenvalues. So we say it has some sort of lower bound of some sort. If the eigenvalues are all bounded below by minus lambda, that's a lower bound on the Ricci curvature. Well, we can say it has an upper bound if just the whole norm of the silly thing is, say, bounded. So the eigenvalues, say, are bounded above and below by lambda. And then, of course, the third condition is Einstein, which is simply to say that the Ricci curvature is precisely equal to a multiple of the metric. Okay. So hopefully, if we do a good job, what we're going to do over the next couple of weeks is try to understand a structure theory for these spaces and a regularity theory for these spaces. If this is supposed to be some sort of a nonlinear elliptic equation, then if it solves something, we kind of hope there's a regularity theory associated to that, and we're going to try to work our way up to that. So in the case of a lower Ricci curvature, we'll be talking about stratifications. In the smooth case, quantitative stratifications. For limits, it'll be just the stratifications of the limit space. And in these cases, we'll be talking about things like a priori curvature bounds on the manifolds. If we're very ambitious, I'm thinking to work our way up in the last couple of days of next week to codimension 4, but this might be ambitious. I'm not sure we'll really get there. This week, though. So what are we going to do this week? This week will be more the nitty-gritty. We kind of have to understand the basics before we can try to jump into anything particularly advanced. So let me sort of outline what the lectures are going to look like this week. I'm going to start with actually just saying 4 out of the 5 lectures because I think it's a little ambitious and I really want to, all these topics must be discussed. So if we don't go quickly enough, our 5th lecture will be just making sure we cover all of this stuff. Otherwise, we'll do something fun on Friday. So today's lecture will be mainly a review of distance functions and the Laplace comparison theorem. Tomorrow's lecture will cover the back-Riemann conditions, and we'll start to review Gromov-Hausdorff convergence. So what I can say is that Laplace comparison and volume comparison, if we get to that today, this is sort of, Ricci curvature kind of controls 2 things about our manifold. It controls geometry and it controls analysis. And on the face of it, these things look quite different, these 2 controls. They are really 2 sides of the same coin, but it's pretty hard to really understand that without getting a little deeper into it. The Laplace comparison, the volume comparison, this is going to be kind of like the geometry of Ricci curvature. And the back-Riemann conditions are going to be kind of like the analysis of Ricci curvature. So this tells us all the basics we need to really take those next steps and try to understand something more. Our 3rd lecture will be on rigidity theorems. So this will include things like we'll prove carefully the splitting theorem and talk about volume rigidity. And if there's some time, we'll probably outline some structure theory for spaces with lower Ricci curvature, where we really won't be in a position to prove it, but to give some motivation as to why people might care about such things. We'll see how really the structure theory really, it comes down to things like splitting theorems and rigidity theorems. This holds actually not just for Ricci curvature, but if you want a good regularity theory for any nonlinear PDE, it's all about rigidity. It's about finding situations that force good behavior on your solutions. So this will be the starting point. And lecture 4, this will be on epsilon regularity theorems. So we'll start by sort of, what's an epsilon regularity theorem? Epsilon regularity theorems are in some sense the first real bridge between this condition and this condition. So in fact, although this is not so obvious at first, almost everything that you prove is about this guy here, lower bounds. And then to get from here to here, you want an epsilon regularity theorem. In short, being highly imprecise, epsilon regularity theorems, they're a way of saying that if you have weak control, well, weak control plus this equals strong control. This is how you prove things. And we'll start by kind of stating the sort of the latest epsilon regularity theorems that are out there right now, and then we'll sort of pick one that's sort of at the base of it all and prove it very carefully. That'll be more or less the basis of most of my lectures. I'll state a whole bunch of stuff, and then, we can't possibly prove everything even in 2 weeks, and then we'll prove maybe 1 or 2 sort of very representative cases that kind of get to the heart of it, even if hopefully with less technical details than some of the others, and really prove that with some care. Okay, so let's start, if I don't lose my notes. So, distance functions. So I'm going to kind of assume we've seen this. I'm not going to prove any of this about distance functions carefully, but I did it. It's an excuse to introduce terminology we're going to be using for 2 weeks, so why not? So we'll kind of crash course a little bit what it is that's important about these things. That'll be helpful. So starting from the very beginning, we start with a Riemannian manifold. So what's that mean? G here, it's a symmetric positive definite 0,2 tensor. Takes 2 vectors, gives you a number. What it really means is that you take 2 elements of your tangent space and you give your inner product. That's it. We're defining an inner product at each point. What do you do with this? Well, the first thing you want to do is you want to define, to get to a distance function, you go from this to length of curves. So that is, if we have some sort of nice smooth curve, smooth, Lipschitz, whatever, it doesn't really matter. Then we define its length. Which I might also write like this. To be the integral of the norm of gamma dot, which itself, by definition, is the integral from a to b of the square root of g of gamma dot. So pictorially, what are we saying? We're saying that we have some curve. At every point, it has its tangent vector, gamma dot. What does g give us? G tells us, this is a vector, so it tells us what the length of this vector is. And what we do is we simply integrate along the curve its length. That tells us the length of the curve. The length of the curve is simply the sum of the length of all of its tangent vectors. That's it. But this happens to give us a way of defining distance. So given 2 points, x and y, we now have lots of curves connecting these things, right? We take our favorite collection of curves. Maybe here's some gamma, maybe here's another, whatever. and we look at the nth overall gamma of the length of gamma, where the nth is overall curves connecting x and y, of course. That's it. So the distance should just be the smallest possible sort of length of a curve that it takes to get from x to y, and that's the distance. And we call a curve a geodesic, or to be exact, gamma is a unit speed minimizing geodesic. If the distance between gamma of s and gamma of t is always equal to t minus s. So that means that if we have some curve here, then in fact, not only does gamma have the property that it does actually minimize this length between x and y, but between any 2 points in here, it also minimizes. So it's the best way of getting from x to y, distance-wise. If you let it just be a multiple of t minus s, then you can drop the unit speed part. And if you have a curve which just locally satisfies this, then you can just call it a geodesic and not a minimizing geodesic. Equivalently, but this is a theorem, of course, that one has to prove. Gamma is a geodesic if it satisfies that the covariant derivative of its tangent vector is 0 in the direction of the tangent vector. Locally, right, this is a second order PDE and gamma, ODE and gamma, right? So you can solve this thing. This is how you get a local existence and uniqueness of geodesics. So let's give it a basic definition here. So we want to call a Riemannian manifold complete or geodesic complete. If for every point in M and every tangent vector at that point, there exists a geodesic from 0 to infinity into M, such that it starts at x and moves initially in the direction of v. So basically, just using the fact that a geodesic solves a second-order equation, it's actually not so hard to see that given any, complete or not, given any point x and any v, we can find a geodesic that satisfies this from 0 to some epsilon at least. Some distance it can go out. Geodesic completeness is the fact that every geodesic keeps going forever. And it's a very nice theorem, the Hoff-Lino theorem, that geodesic completeness is the same as metric completeness. So we have a distance function here. We can talk about metric completeness, right? So Cauchy sequences converging, blah, blah, blah. And this is the same thing as being geodesically complete. Okay. So basically, from this point forward, we're always going to assume geodesic completeness. This is not necessary. One can avoid this assumption, but it just, it avoids technical complications, so why not? Nice erasers. All right, how are we doing? We got, I think, 2 more sort of basic definitions to do, and then we get to move toward proving stuff. Very good. So once we have something geodesically complete, what can we use this for? So the first thing you should use this for, if you're doing geometry and you're starting geometry the first time, The first thing you have to do is connect what it means to be a manifold to what it is to having a geometry. That means you want coordinate systems that are somehow well behaved, they see the geometry well. There are many ways of doing this, and we'll discuss more than one of them. So one's the exponential coordinates, which we'll introduce right now because it follows pretty easily from what we've said. And the other which are harmonic coordinates, which we'll probably do on lecture 4 when we're talking about epsilon regularity theorems. So definition. So M at this point, right, is a geodesically complete manifold. So we can define the exponential map at some point as a mapping from the tangent space of that point. So this is like Euclidean space, right? It's just a mapping from some Rn to M by the exponential map at x evaluated at v is just equal to gamma xv of 1. Where gamma is a geodesic, which, as you might guess, starts at x in the direction of v. So it's a way of taking the tangent space onto the manifold, and by mapping to geodesics, using geodesics to connect the tangent space to that manifold. And now we get to actually the reason why I went through all of this is that I wanted to find the critical set. So that this will play a hugely important role in the Laplace comparison theorem. So I mean, now that we have a distance function, we're going to be looking at the Laplacian of the distance function because this is going to be our first connection between Ricci curvature and controlling the geometry. And what's going to happen is that we're going to look at this Laplacian. And this Laplacian, I mean, it can't possibly be a smooth guy because the distance function is not smooth. But it exists as a distribution, and it'll turn out to be a measure. And this measure is going to be concentrated on the critical set. And we had to find out where this bad set was, and we had to go through all this to do that. So the critical set definition. Actually, I can start it over here. So given x and v, let L sub xv be the maximum t such that our geodesic starting at x in the direction of v restricted to 0 to t is minimizing. Let's draw a picture real quick. Right? So we're picking a point x. We're looking at a direction v. We're saying, here's our geodesic gamma in that direction. And you can prove, it's not so hard, that this geodesic gamma is always minimizing, at least for some short time. Always true. And so what you want to do is keep going out until it stops being minimizing. So at some point, you get to a point out here where if you go any further than that, well, it's still a geodesic. It solves an equation. But there's some other geodesic that gets there faster than this thing. Right? So this point here, which we'll call LXV, is that maximum length that you can go while it's still minimizing. And our critical set at x is by definition going to be the set of y and m, such that y equals gamma xv of LXV. So that is, at every single point, we go out as far as we can. We stop when we can go no further. And then we union up all those points, right? So for every point, direction of the tangent space, we get some such thing. Right? What we end up getting here is the critical set. For instance, if we're on a sphere, right, then if you take any point, the critical set is the antipodal point on the sphere. Because every geodesic is minimizing until it gets all the way around the sphere. But then if you go further, it's clearly not minimizing anymore. You could have gone the other direction around the sphere and gotten there faster. Right? So it's a nice, simple guy. In principle, you kind of want to view this thing as being some sort of codimension 1 hypersurface inside your space. You can actually make it rigorous that that's, I'm going to use the word rectifiable here, but don't worry about that. It's a well-behaved thing. But well-behaved or not, it's not really meaningful to us. This is the definition. We're fine. Now, what do we need to know about this set to prove stuff? So let's just collect together all the basic, and you can find this in, this is in Jost's book and Peter Peterson's book. This is the basic sort of structure of distance functions you can find in pretty much any good introductory book on Riemannian manifolds. So first, take any point x. Let's look at our manifold and get rid of the critical set. So the problem is that we don't know how badly behaved this is right now. A priori, if I tell you nothing else, it can practically be the whole thing, or at least densely distributed, or some sort of really awful-looking object. But the point is, in fact, that if we take our manifold and we throw away the critical set with respect to that point, then what's left over is open and dense. And star-shaped, in fact. So what's star-shaped mean? It means that if I take any points not inside the critical set, now if I look at a minimizing geodesic connecting x to this point, so this is inside M minus the critical set, then that geodesic is unique, and every point along this is also not in the critical set. So it contains all geodesics that are actually inside it. So if a point's inside this set, so is the geodesic going from x to that point. Very well-behaved set. Second point we need to know, if we look at the exponential map at x, and we restrict ourselves to the collection of v, wait, what am I saying? Just say it this way. We look at M minus the critical set. We look at its inverse image inside the tangent space. And so these are the set of points up in the tangent space that map onto these things. And then if we let this map back onto the critical set, we get a diffeomorphism. Diffeomorphism now. So this is the statement that this is an actual coordinate system now for M onto an open-dense subset of M. Right, so the exponential coordinates, they don't just define coordinate systems, they cover almost everything at every point. An open-dense subset of your manifold. And the final point we're going to need here is that the distance function centered at x, so with x fixed here, we're kind of viewing y as the variable, is smooth on M minus the critical set. So our distance function turns out to be, it's always a Lipschitz function. Its Lipschitz norm is 1. But it's an honest, smooth function away from this closed set of measure 0. That doesn't cover very much. So it's smooth almost everywhere. And finally, and this will be the end of our review, this is just a definition. This is the end of our review. Now I make a definition. We're going to call the R critical set centered at x, just to be the set of y, such that y is equal to gamma xv of. So that there would have been the critical set, but now what I'm going to say is we can move a little bit below the critical set. So what I'm saying here is that if this here is our critical set, the R critical set is just something that pushes away from it by a little bit. So as R goes to 0, it covers an open-end subset of the manifold. And note that the interior normal to CXR satisfies the following super important condition. We're going to use this in 10 minutes for a good deal of Ricci curvature theory would be wrong if this was not correct. Satisfies that the normal in our product with the gradient of the distance function from x is positive. So let's draw a picture of that. What I'm saying is we have our R critical set. So this takes our critical set and pushes us back into the smooth part a little bit. We look at the normal here, and let's draw a picture that makes it not quite look like they're the same thing. So our normal here is maybe more like this. So just our normal vector to our surface. And if we look at the distance function, then what's the gradient? The gradient of the distance function, right, that's just the tangent of the geodesic going from here to here. And what I'm saying is that they always point in the same direction. Okay. Yes? That's right. I mean, I guess R could be 0, and then you just get CX, right? If that's what you're... That's right. Instead of going as far out as you can go and being minimizing, we go as far as you can go, but minus some R. Just pushing a little bit.
So you know that for all, it's bounded uniformly away. It's bounded uniformly away from 0.
Yeah, that's right. That's the theorem. So the point is that there is an epsilon at every point for which it is minimizing. That one's got to prove that. Right? I'm taking that for granted for sure. That this is all crash course here. All right? That will absolutely be proved in Yost or Peterson. I'm going to say it doesn't really matter. I'm going to want it to be, I mean, it just depends on whether you want it to be an open or closed set. The boundary is the same either way. So it's however I wrote it, it's how I'm going to do it. It can be open, say.
Maybe we should put a boundary on the last line, normal to the boundary of CX.
Thank you. Maybe that was the point of confusion. The boundary. Thank you. Right, so CXR here is this, right? It's this region here. And the boundary is the piece there. Okay. For any points of real confusion, your TAs will be happy to study this and answer them for you. Great. Okay, so this is our crash course on distance functions. Yeah, I was pretty sure this lecture was going to be a long one. Those 4 lectures will certainly take 5 days at this rate. But that's okay. That was expected. Okay. So what? So with the basics of distance functions down, we know how to define distances between points, and we know some basic nice structure about distance functions on manifolds. They're smooth on open-end subsets, so forth and so on. What can we actually say about the distance function? And in particular, what relation, I mean, obviously, the distance function has some relationship to geometry. It is geometry. But more importantly, it actually has some relationship to Ricci curvature, which on a first glance is maybe less obvious. To understand this, let's actually just look at an example real quick. We've had lots of theorems floating around. Well, what are the easiest examples of Riemannian manifolds? The most basic ones are the space forms. So M and K, this is be the simply connected. The word "the" there is really a theorem, but that's fine. Be the simply connected. N-dimensional. Manifold. With sectional curvature. The constant K. So it's fun that we can actually write this example out completely explicitly. So there is, in fact, one, I mean, if you pick a dimension, you pick a K, there is up to isometry a unique Riemannian manifold, which is simply connected, has dimension n, and has constant curvature K. And through a warped product construction, we can write it out explicitly here. So let's write the metric. G and K so topologically, I'm going to write this on Rn now. So it'll be in polar coordinates, it would look like dr squared plus some function, which I'll tell you explicitly. Times the standard measure on the n-1 sphere. So this is standard polar coordinates with some work made factor. To the -1/2 sinh of k1/2 r if k is negative, r if k is 0, and k to the -1/2 sine of k1/2 r if k is positive. So what does this mean? This means, so k equals -1 is hyperbolic space. K equals 0. I mean, this should be a really good exercise to see how much I've lost you. So if we were to write the standard metric on Rn in polar coordinates, what we should get in front of this thing is an r squared. In other words, this guy here. So that is to say, it's just Euclidean space Rn. It's a good exercise to do. In fact, computing the curvature of these guys is a wonderful exercise in actually understanding that you're getting a constant out of it. It lets you know where you're messing up in your computations because it'll take you 10 times the first time through. And k equals 1 is the sphere. Sn. So looks like this thing here. So hyperbolic space is basically expanding out faster than Euclidean space, and then we have Euclidean space, and then we have something that's sort of bending in faster than Euclidean space until it goes all the way around. I mean, sort of imagine subtracting this point here, right? It becomes like Rn now, but the metric sort of curves back down until it closes up and gives you Euclidean space. So it's a nice simple example. But now, why is this example fun or relevant to actual geometry? So a nice computation to do is the following. On our space, pick a point, your favorite point. Look at the distance function and compute its Hessian. You get a 2 tensor. So what do you get? So this is this is like an n by n matrix at that point, right? It's a 2 tensor. What you're going to get is that it's 0, and this is in the direction of the gradient of the distance function. So if we pick our point x, we have our point y. We have a distinguished direction here, which is sort of like the gradient of the distance function here. If we're on the smooth, well, it's all smooth here away from the polar piece. So if we break our tangent space up by looking in this direction and looking at the perpendicular directions, then in this direction we just get 0. And in this direction, you get that it's given explicitly in terms of these functions. So it's a multiple of the metric in the directions perpendicular to here. In particular, the Laplacian of the distance function. Well, that just means that we're tracing, right? So we just sum up over all these directions. So this is precisely equal to n minus 1 times some function of the distance function. The idea is to use this computation as motivation for sort of wanting to say something about the Hessian or Laplacian of distance functions on any Riemannian manifold. I mean, we're going to use the Hessian and the Laplacian of the distance function to prove all kinds of nice structure theorems about these spaces, but we need it to be controlled in some sense or another. And in fact, the first real theorem that we're going to prove, and my goodness, I'm going slowly, so we may finish this tomorrow, is the following. And this is the first connection between, say, Ricci curvature and geometry. So let's say this carefully. So let's let Mg be a complete manifold. Remember, that can mean either geodesically or metrically. They're the same thing. And let us assume the Ricci curvature has a lower bound, bound it from below by minus n minus 1 times k. Why is that? I mean, why am I normalizing by n minus 1 here? Well, the point is that if this has constant sectional curvature k, then the Ricci curvature is going to be the trace of this thing. And if we trace that out, that means the Ricci curvature is exactly equal to n minus 1k. Remember, when you trace here, you can only do things that are perpendicular to stuff. So you get an n minus 1, not an n out of it. So this is sort of like what the Ricci curvature of the space form of dimension n of curvature k would be. So we're kind of hoping to use that as a basis to say, well, if this thing has its Ricci curvature bound from below by wherever the Ricci curvature of this object is, then maybe we can use that as motivation for a statement. Now, then what? Then let's look at the Laplacian of the distance function centered at some point. So first off, what on earth do I mean by that? So, well, this thing is smooth away from some small closed set, right? So certainly we have no issue whatsoever in making sense of this on that set there. But this is nowhere near sufficient to prove theorems. Well, what I really mean by this thing here is that you can take your favorite function in the world and compute its Laplacian, right? You just mean in the distributional sense. Every function has a Laplacian. It just doesn't itself have to be a function. And I could wave my hands past this point, but I sort of decided that so many books wave their hands past this point that it should be done carefully somewhere in your life. So we're going to do this carefully. So the Laplacian of this thing, in the distributional sense, is not just any distribution. What's a distribution, right? It's something that acts on a smooth function and gives you a number. So, I mean, examples that I could evaluate a function at a point. That's a distribution. I could look at the value of its derivative at a point. That's a distribution too. What's the big difference between those two distributions? Well, the first one's a measure and the second one's not. So somehow, the best type of distribution is a function, something that you multiply and integrate. I mean, that's what we really like. We'd love it if this thing were just a function. That's not true. On this critical set, where this thing is not smooth, there is an honest-to-goodness piece of this Laplacian, which is non-smooth in nature, and it's a distribution. But as a distribution, it's the best possible distribution. It's a measure. It means that you act on the function just by integrating the function with respect to some measure. I mean, you can't really get better than that if you're not going to be a function. So it is a measure, which I'm going to call mu. And I'm going to break it up into two pieces, the absolutely continuous piece and the singular piece. So what's the absolutely continuous piece mean? That's the function part. Right? That's the part of the Laplacian here that is an honest function. It's the part of the distribution where you are just multiplying by a function and integrating. And the singular part is the part where this is a measure that's more complicated. Like we're evaluating at a point, or we're integrating along some hypersurface inside the thing. This is not the end of the theorem. What's this again? The Riemannian volume measure. The Riemannian volume measure, DVG. With. Well, there's two statements here. So the absolutely continuous part. So this is the part that's like a function. So we don't know exactly what it is. It's the Laplacian of the distance function on the smooth part. That's all it is, right? So it is just the Laplacian of the distance function on M minus the critical set. So this is wherever it is smooth. This thing is literally just the Laplacian. We compute the silly thing. But there's the lovely point that it's actually bounded from above by, and this is where the Ricci curvature comes from, by the Laplacian of the distance function on the corresponding space form. So on the smooth part, we can compute the Laplacian, and we actually at least have an upper bound for it. It behaves at least to an upper bound approximation like the Laplacian on the corresponding space form. There's nothing complicated in this. I mean, this is a smooth thing. We take its Laplacian, and we're going to evaluate that it's actually bounded above. That's all we're doing here. And the singular part, the scary part of it, well, we do at least have one really nice thing about it. Is a non-positive. So that is to say, it's less than or equal to 0 measure supported on the critical set. Okay. Okay, so I think, because regardless of whether you have much interest in Ricci curvature or not, that this computation here is extraordinarily important. Knowing how to compute Laplacians of things in distributional sense, knowing how to see if it's a measure, when it's a measure, how to prove it's a measure, how to guess such things and actually show it, and how to estimate it. I mean, these are just simply important things you should know regardless of what your interest is. So we're going to do this carefully. We were supposed to do it carefully today, but we'll do it carefully today and tomorrow. Okay, so clearly there's two aspects to the proof of this. One is that we want to just simply compute the Laplacian of the distance function on the smooth part and see that we have this upper bound. This is somehow the less scary part. I mean, there's an obvious proof there, but we're working in the smooth world here. There's nothing else going on. And the second part is that we need to see that when we consider this thing as a distribution, that what's left over is an actual measure which is supported on the critical set. So we need to break it up into our two pieces. I think we have enough time to at least prove this piece today. And for that matter, just to make things less complicated, we're going to assume this is non-negative Ricci curvature. It's not just some lower bound, but non-negative. The proof in the general case is exactly the same, but we have less complicated functions going around. Because it simply means that the Laplacian of the distance function is less than or equal to n minus 1 over the distance function. Nice, clean something. And the proof of the other case is verbatim. I mean, there's nothing being hidden. It's exactly the same. Okay, so how do we do this? Yeah, so that means Ricci is non-negative, right? Just to simplify the functions involved, nothing else. So what do? We have our manifold. It's got non-negative Ricci curvature. How does Ricci curvature play a role in this? I mean, this is what we really want to see from this proof. Pick our x. This is where we're going to look at our distance function from, and pick our favorite y. Now pick a minimizing geodesic connecting the two. Here's gamma of t. So now what we're going to do is let's look at the Laplacian of the distance, but just evaluate it at each point along here. So we look at the Laplacian of the distance function from x, evaluate it at gamma of t. So this is just a real valued function on R now, nothing else. And what do we want to do? We want to compute its rate of change. What's ddt of m of t? Well, given what this is, that's just equal to Well, it's the rate of change of this function in this direction, right? But so this is the rate of change in the gamma dot direction of the Laplacian of the distance function, evaluated our gamma of t. But, I mean, what's gamma dot? That's exactly just that's just the gradient of the distance function from x. So it's just the gradient of the distance function to the So it's the gradient of the Laplacian of the distance function in the direction of the gradient of the distance function, evaluated at gamma of t. Fine, no problem. It's a nice statement. Let's keep the statement and go over here. So let's write this in coordinates. Everything is smooth here, right? So there's, for t positive, everything is smooth. There's no real fear of anything. So writing this in just some sort of coordinate whatever, we get that we can write this as dA of the distance function times dA. And what's the Laplacian? It's just dB. It's the trace of the distance function. Picking our favorite coordinate system. It doesn't matter what it is whatsoever. It's dAd. Now, what's the interesting part? Where does curvature come from? I want to take these two derivatives and switch them. So I want to write this like this. And if this were Euclidean space, we'd be done. This is not Euclidean space. You get an error term when you switch covariant derivatives. The error term is curvature. So this is dA of d times the curvature. As a forward tensor, it's A, B, B, and then you have to grade it in the c direction. Your homework should be basically to do this proof 5 times, right? I mean, get comfortable with the notation. What is Ricci curvature? Well, I mean, so this thing here, right, is just equal to minus, if I want to switch these two, BA. And then the Ricci curvature is just the trace of these two things. So this is just Ricci. So this whole thing here is equal to dAd, dB, dB, dA, d. Notice I switched these two, but there's no error term because we haven't gotten to the part where we're taking a second covariant derivative of a vector. So you're allowed to switch these two. Minus, well, this becomes the Ricci curvature. And I can trace with both these guys, or I can just write it like this. Gradient d, gradient d. But what's this? So this term here, the Ricci of some direction, it's bigger than or equal to 0. I mean, that's the assumption. So I can drop that term entirely and do that. And I can just leave this term. And if I leave this term, then I can pull this dB out, like this. dAd, d, dB, dAd. But then I have to subtract off what it is that I actually got rid of. So this is minus dB, dAd, dB, dAd. I got 1 minute. It's okay. So now what's the clever point here? The point is that that first term there is what? So that's just equal to the, if I pull the dB out, I can rewrite this as 1/2 the Laplacian of the norm of the distance squared. Because this term here is just dB of dA squared, 1/2. But what is this on the smooth part? What's the gradient of the distance function? It's always 1 on the smooth part. So if I take derivatives of it, I get 0. The second term left over, well, that's minus the Hessian of the distance function squared. The Hessian of the distance function always vanishes in the gradient direction. And now what do you know about matrices? Just take an m by n matrix. Doesn't matter, right? The norm square of that matrix is always bigger than or equal to the trace of it squared over the dimension. Standard fact about matrices. So just apply it to this, and we get minus the Laplacian of the distance function squared over n minus 1. But what's this? This is just minus m squared over n minus 1. So what we've proved is that if the Ricci is non-negative, then m dot plus m squared over n minus 1 is less than or equal to 0. But this is precisely equal to m naught dot plus m naught squared over n minus 1, where m naught is simply equal to what it is that we're trying to bound by, n minus 1 over t. Right? We're trying to show that m is less than or equal to this. And we know that this equation is less than or equal to the solution of that equation. And now it's maximum principle. I'm skipping the last 5 lines because I've got no time. But maybe your TA can finish the last 5 lines. Once you have an inequality like this, you can use a maximum principle to actually finish it. So what that means is that this implies, that m of t is less than or equal to m naught of t. Which is the proof. Okay, homework, do it 10 times. I'm done.